is set up and knows how to run the slides.
Maybe. All right. Well, thank you for the opportunity to tell you about the LDEX results. I'd like to walk through the expectations and notice that a couple of slides will say Lunar Science Forum 2013. That's intentional. I brought a couple of slides from a year ago, what our expectations were at the time. And then hopefully we'll change over to what actually we found. So the expectations and then the instrument, principle of operation, how we test and calibration a dust instrument. And I tell you about the results, the dust ejecta clouds. No doubt we have seen it, we have found it, we identified it, and what we have about, what sort of a statement we can make about the lunar horizon glow. That was also of great interest to this mission to figure out this historical artifact back from the 70s. High altitude dust that appears to be, or people suggested that appears at over the terminators. Oops, that's not it. Now it's interesting because I don't see anything. Oh, there we go. Perfect. So that's a slide from a year ago. What we thought we're going to find about the lunar dust cloud. We believe that there will be more or less a spherically symmetric, continually present ejecta cloud that is generated by interplanetary dust impacts. Any airless body that is exposed to interplanetary dust will generate secondary particles, and we were hoping to see that. We are expecting that once in a while the densities or the impact rates skyrocket, because probably we'll see meteor showers. And then we're also expecting density enhancement of small grains over the terminators. This is the one that relates to the horizon glow. The ejecta clouds, of course, these are bound particles that the impact generates particles, most of them with speeds below escape speed, and they just follow ballistic orbits. The first time we all have seen this is the icy moons of Jupiter by Galileo. There were flybys, and during flybys of the icy moons, the number density of dust or the impact rate went way up, and people worked out models about the ejecta cloud based on maybe 400 hits that they found through all the icy moons at Jupiter. We collected 140,000 hits in the period of operation of LDEX. But the expectation is that over the surface, the density is increasing. I have to remind you that this was in units of planetary radii, and we are operating much, much closer to the surface than the Galileo flybys were. So the observation and the model about the horizon glow, people argued there must be an enormous amount of maybe tenths of a micron dust particles over the morning terminator, because the Apollo astronauts, as they came towards the local sunrise and took images of the sun, they argued for extra solar brightness that is probably due to dust. So here we were, our assignment was to figure out what that might or might not be. Oops, when you are proposing an instrument to NASA, of course, you have to have a model, what sort of expectations you have, what sort of impact rates you have, what's the right size, what's the right sensitivity of the instrument. And at the time, we argued that imagine a 30 by 100 kilometer orbit as a function of local time. That's the orbit. And I'm sorry you can't see it, but the purple density is slowly dropping. Those are the ejecta clouds, and then these ears are over the morning and evening terminators. Those are the tiny particles. And you could fly through and predict an impact rate. Lottie followed a trajectory with rough speeds of about 1.7 kilometers per sec with respect to the surface. You could turn that into a number, how many per minute you will see. And we argued that you will see on the order of 1 to 10 at 50 kilometer height or so, and a whole lot of tiny ones. But the tiny ones hitting us at 1.3 kilometer does not generate enough charge to trigger. I cannot measure them directly. So we have a mode that is dedicated to the collective signal of a lot of small particles. And that page must look familiar. There are measurement requirements, and the measurement requirements state how sensitive you have to be for single gate detection, how sensitive you have to be for collective signal detection, a lot of small hits all at once. Here is the instrument. It's an impact ionization dust instrument. A lot of heritage of this type exists from Ulysses and Galileo and Cassini. It's a hemispherical target. The dust particle flies in. 1.6 kilometer, 1.7 is big enough to generate a cloud of electrons and ions. The electrons are collected on the target, and the ions are collected by this electric field that focuses them on the multi-channel plate. The multi-channel plate can trigger on a big enough signal, or automatically every tenth of a second we read out how much current it collects to identify the collective population of small grains. The way we calibrate an instrument like that, at least for particles that are big enough, is to use a dust accelerator. This is 3 million volt electrostatic accelerator. It shoots a dust beam, and then in the beam line we have pickup tubes that would tell you the speed and the mass of the particle precisely, and we can divert it out of the beam if that's not what you want, or keep it in the beam if you want. And the waveforms that we collect from the target and the waveform that we collect for the multi-channel plate encodes the mass and the speed of the impactor. The amplitude of this signal knows about the total mass, and the rise time of this signal, I will show it in a second, knows about the impact speed. If you can't see the date, that is 2012, before we delivered this instrument, and that is a pair of waveforms that we collected in 2014 while we were in space, comparing the amplitudes, the waveforms, the rise times, the decay times. We can hopefully identify dust impacts with great confidence. So here is how the instrument is calibrated. I'll show you the impact charge over mass and the speed. It's a nice tight curve. There are a couple outliers. Those are probably grid impacts or wall impacts. And that's our error factor, m over m naught. We could tell you the mass of an impacting particle within a factor of 1.6. So we can confuse a 1 micro or autogram particle to 1.6 autogram particle. But that is still perhaps one of the best error factor for a dust instrument ever flown. From the rise times, this is now the rise time in microsecond. That's the speed. We can establish a similar curve. So the way that waveform looks, we can read out the speed of the incoming particle. So what we found, perhaps this is the crucial plot. Time runs on the x-axis. Here I'm showing you the impact rate per minute, and the bottom we average the impact rate per minute for a whole day. Impacting a surface is a stochastic process. You release a burst of particles. Once in a while you are lucky and you fly through the burst. And that's of course in response to the general background of dust particles that about 5 tons of them, based scaling from the Earth, hits the moon day in, day out. Once in a while, these impact rates sustain for a whole day or several days. That's what we think has to do with meteor showers, where the influx is elevated for a set period of time. And the next talk, Jamie will tell you how we can identify the properties of the Geminites and some of the other meteorite streams that happen during the LDEX mission. So even though there are a lot of variations in time, in space, I would like to share with you what I think is the global or the average dust exosphere of the moon. Here it is. This is height running from 0 to 250. And this is the density in units of 10 to the minus 3 cubic meters. And as you go closer to the surface, the density goes up. And then as you move away from the surface, the density goes down. We only spent at the initial 1 month commissioning period between 200 and 250. And the total amount of time, the black line is tell you how many hours we spent at a given height. And the blue line tells you the number of events that we collected. And then you could imagine, if I know what sort of volume the dust instrument carved out, the impact rate can be turned into densities. And that's the top plot. The error bars are naturally very large from regions in space where we have very few events. You could turn it some sort of an atmospheric plot. This time altitude is running on the y-axis. And this is density, again in units of 10 to the minus 3 per cubic meter. The width of the color bar shows error, And these are the cumulative densities of particles bigger than 1.1 micron, particles bigger than 0.6, and particles bigger than 1.1 micron. There is a nice kind of a dust exosphere where the density seems to have some sort of a scale height dropping with the altitude from the surface. All right, so let me tell you, if we collect all particles that we hit between 0 and 5 and 100 and 105, what's the size distribution? Seems like a parallel. Peaked, of course, somewhere around the threshold. That's the smallest particle we can detect. And luckily, look at that. The speed distribution peaks at 1.7 kilometers per sec. That's the spacecraft. So the most simplistic model of all, that particles are ejected with a size and speed distribution that are independent from the surface with a small, relatively narrow cone angle, and they just move up and down, and most particles that I detect are at the turning or the highest point at their trajectory. Certainly at that point, there are no slower particles because they don't make it up there, but there could be an abundant population of faster particles, but the speed distribution is a parallel, so there's much fewer of them. So as a first go, we can analyze, and that's how we analyze the data. We assume that we are detecting particles at the highest of their trajectory, and I'm telling you how this model works. Well, not so hard. This is the definition of the mass distribution, cumulative mass distribution with a parallel, cumulative velocity distribution with a parallel. I didn't try, there are 5 parameters you could play with. I simply moved the yield up and down a little. So it's not hopeless, but we are not quite there yet. We didn't quite figure out what to do. Also, interestingly, we had about 80 days of total on time. We devoted 4.5 days of turning this instrument anti-RAM. In theory, we couldn't detect dust at all. Certainly not the type that is at 0 relative speed to the moon, because we are pointing backwards. But we did detect, we have about 60 events of, from this period backward pointing. If I scale that with the amount of time that we spend this way versus the RAM direction, it's about less than 5% of the number density that seems to be ejecta particles that are very fast and that coming at a shallow angle. They have to come at a shallow angle because otherwise they would not make it into the detector. And I have to wrap up, and this is hopefully my last, not the last slide, but let me get to the last slide. And I didn't tell you about the horizon glow. We found no evidence. I cannot tell you that there is a horizon glow. It seems that there is none high latitude or high altitude particles. But what I would like to share you that everything was delivered as required. And this is the last slide. There is a dust exosphere. We found no evidence of levitated dust particles. It's wonderful to find the ejecta cloud, but I think what we are after now, that you could use the dust to learn all kinds of other things. It's not the end of the story. It's almost like a new chapter in planetary science that you could learn about the surface. Maybe the composition, if you fly a more sophisticated instrument, maybe the geotechnical properties. You could learn a lot from the ejecta clouds. Also, when big particles hit, hopefully that never happens to the spacecraft, but we see the plumes from them, and we could build much better hazard models for particles that would be hitting a spacecraft or a mission would be an end of mission scenario. Thank you.
Have time for one quick question? Carly.
For when you saw the peaks during the meteor showers, you implied all of those were ballistic from the meteorites hitting the moon, and you were seeing the moon material that was there. Could you have seen any from the meteor shower directly, do you think?
So we could do that calculation. The incoming speeds are quite high, tens of kilometers per sec. So maybe we do have a lot of, not a lot, we have a handful of signals that fully saturate both the target and the MCP. They could be very large, very fast particles. We do have a few of them. Possibly they are the incoming high speed, but your effective area very quickly drops with the impact angle. So it's difficult.
You were never going backwards.
I have to check. And even if it backwards, Anyway, we have to work out the geometry. Possibly there are a handful of hits from incoming particles.
Okay, well, thank you very much. Sorry we don't